Hey guys, what's up? My name is Gabe and this is Games with Gabe. This is the next episode in coding a 2D game engine in Java series. So in the last tutorial what we did was we covered game cameras and how you can use transforms, specifically view matrices and projection matrices to create move the world around the camera, basically, sort of like what we did in our previous series. In this tutorial we're going over shaders, and we are going to be going over how to upload shaders to the GPU and then talk a little bit more in depth about how the shader programming language works, the different sort of keywords that you should look for and what they mean, and what you can do with them. So we'll be doing something cool, which should be showing right now, hopefully, and that will just sort of show off what you can do with shaders. They are really cool pieces of technology that can be used for literally anything you can think of, and we will take a look at them today just to see what we can do with them. So let's figure out how they work and get that done. So I figure the best way to try and understand shaders is to use a drawing and a little bit of diagramming. So I have right here a little shader program that doesn't really do anything. This would be the vertex shader, and you can tell that because it has these layout things, which will explain what all this is. So remember we talked about how graphics programming works, and we said we have these things called VAOs, vertex array objects. And what this contains is a bunch of attribute pointers, right? And we define these attribute pointers inside of our big vertex list, which means like, oh, we want attribute 0 to be X, Y, Z for our position. We want attribute 1 to be U0, U1 for our texture coordinates, so on, so forth. And so we sort of define the way these things work using GL vertex attribute pointer. And we say, okay, we want 0 to contain these three, and then we want attribute pointer 1 to contain these, and then a color for attribute 2, so on, so forth. And then what happens is we create that inside of this VAO. Then how do we access all this data that we have buffered to the GPU? Well, we access them through these things called layouts. And so inside of our shader program, the vertex shader, we have this layout parenthesis location equals number parenthesis, and this corresponds directly to our attribute pointer. So you'll notice I've color coded these. The green is attribute pointer 0, the red is attribute pointer 1, the blue is attribute pointer 2. And then these could be any type that you want. So you just have to make sure that they match the types in here. So in this case, I have a vec3 for location 0, a float for location 1, and a vec2 for location 2, which means we could not have this u2. It would just have to be one variable. And then for the last one, we would have to have a vector 2. So we'd have to have two floats inside of there. And so the way that the GPU knows this is because we've already specified how it can find everything, and then it basically just uses these numbers to sort of index into the array, the data that we've given it, and it's like, okay, I know that the float's going to be in this position in the array, and then it can go and find it for us, and then we can just access it directly inside of our shader program right here. Now, there's this other thing though. What if you have variables that apply to several vertex attribute objects? Vertex array objects. Things like cameras, right? Because the view matrix and stuff, I spelled that wrong. The view matrix and stuff, that applies to every object in your scene, right? The camera position doesn't change from object to object. So typically you would want one shader, and you would only have to want to tell the GPU, hey, we're using this, just keep it there because we're probably going to be using it for a few different things. Then what happens is we can upload it. Okay, so we upload it using these things called uniforms. And so uniforms are these things that stick around, right? So they stick around from object to object and don't have to be respecified. So every time you bind a new VAO, these things all change, but these things only change once you upload a new uniform. And how do you upload a variable to the GPU? Well, the GPU uses IDs, just like we did for all of this stuff here. And so basically what you end up having to do is you have to say, okay, first I need to find the variable's location in the GPU. So you say something like variable location equals, and then you get some function from GL, and you pass it the name of the variable you're looking for. So say we were looking for U color. It would say, okay, I'm looking for U color, and then it gives you the variable location, puts it in here. Then next thing you have to do is you use another GL function, which is like GL uniform and then the type. So uColor is a float, so you would say F4 or something like that. We'll look at it in more detail. I can't remember these. There's so many. But basically you would say that, and then you would say, okay, I'm giving it to this shader. So you would give it the shader's ID. And then you would say, and I am looking for this variable. So you would give it the location. And then you would say, and I'm uploading this value. And then you would give it the value. So that's basically all there is to it. And then what the GPU does is it uses the ID that it has obtained through this. It uses this ID saying, okay, so this is a shader we're looking for. Actually, you would use the shader ID in here. Let's backtrack a little bit. So basically you would say, I'm looking for uColor, and you have to specify the shader you're looking for it in. So then you would pass in your shader ID here, which if you think about it, that makes sense, because why would you look for this uColor if you were looking in a shader that didn't even have something called uColor? So you tell it the shader ID, which is our program that we're looking in, and then you tell it the variable name. Then you do this GL uniform. I think it's like 4F or something, not F4. But you do this, and then you say the variable location and value. And you do have to make sure that in between these two calls, at some point you have said shader.use. So you have to make sure you're using the shader, because this call expects to upload it to the current shader being used. And so if you just pass this in and pass this in, and you don't have some shader being used right here, then it's just get passed into whatever shader was last used, and that variable location might not even exist, and then you could get an error and you have no idea. So between these two, just make sure you call shader.use if it's not already being used, and then you can upload it just using that location. So it's pretty straightforward. It's really hard to grasp when you're first learning this stuff. It was for me, and I really want you guys to understand how all these things are connecting together, because it's not that hard, but if you've never done this stuff before, it can be difficult. And so just really want to hammer home the point. We have these VAOs, which we defined. We defined what these attributes are. We defined them in an array that looks like this. And we said, we want this array to be formatted this way. And then we specified all that format in our code. Then what happens is inside of our vertex shader, we can say, okay, we're getting this location here. We're getting location 1 and location 2, which is going to match up with our VAO. And so then the types would match with whatever types we passed in down here. Then we have these last things called uniforms, which are basically variables that we can upload to shaders. And we just look for the variable's location. First, we ask for where it is in the shader. Then we just upload it to that shader using GL's function. And then we pass it the value. And then the last part of a shader program is the main program, or the main function. The main function is in charge of, it's like the entry point for the program, just like all programming languages have. And basically you just write all your code inside here. And then you end up, for GLSL, you say GL position equals, and then you put some vec4 here. And what that does is that ends up outputting the final position as whatever this vec4 is for this vertex. And then I feel like one last thing that would be nice to know about shaders. So we have these in and these out specifiers. So in means something that you're taking in. So we're expecting these variables to come in through here. Out, you could specify something like out vec3 fpose. And that basically just means you're going to declare some variable inside your main function called fpose. And inside of your fragment shader over here, you're going to have something that looks like this in vec3 with the same exact name, fpose. So for every out you have inside of your vertex, you must have an in inside your fragment shader, because these two are directly correlated. And this guy is going to expect to pass all his outs to this guy's ins. And then this guy has one out, which is the color. So you would just say out vec4 color. And then this color is what gets output to the next stage in our programming pipeline, or our graphics pipeline, and then it continues to go through. Like I mentioned in the graphics programming, this operates on vertex. So this guy is on the vertices of an object, so these would be the vertices. Fragment shader operates on the interpolated data sent in from this. So if this guy passes in position to here, then what this guy gets is an interpolated position between the two vertices, well actually all vertices of wherever it is within the object. So it would get, if if it was here, then it would get this interpolated position, it would get this position, and it gets it all at the same time. So we don't have to specify any of that. It interpolates by itself. It's called a fragment that it's operating on, and this is called the vertex that it's operating on. So hopefully that clears up some things. Let's code this part, and then we'll actually code a shader to do something cool, and we will sort of see how all this fits together. All right, so picking up where we left off, we had that nice camera movement that we were doing inside of the level editor scene. We were just moving this around. And then we did this thing, the upload map4 function. We're going to create a bunch more of these just so that we have all the functions we might need so we can upload any type of variable. Because for every type of variable you want to upload, you need to create an upload function. And if you want to know like the different types and stuff, just look up the GLSL documentation. And then you can just go into here. And so basically this will just tell you all the different documentation and stuff. This is for GLSL4, which should be fine. And then you see you can just go into here. It's got a bunch of built-in functions, tells you all these different things. And then if you want to, Chronos.org is another good source for this stuff. And then this just sort of lists like the different types that you can have in GLSL, which is helpful. Now back to this. So let's go. We want to go into our shader class, which we created inside of our render. And we created this function sort of on the fly. You should understand it a bit more now. What we're doing here is we're saying, okay, get the location of the variable for our shader program. And then what we're saying here is the map buffer. So matrices are the only kind of weird things because we have to sort of flatten them out so that they are actually in a 1D array like this. And this would actually be 16 wide. So what we do is we create a buffer of 16 variables wide, and then what we then just sort of stuff all of our stuff into that buffer using this function. And then what we do then is we say GL uniform matrix 4FE, which is expecting just a 16 long array, and then we give it the location. We say whether we want it to make it a transpose or not, which is a linear algebraic function. We do not, and then we just give it the buffer. So it's the only one that's kind of weird. Everything else should be relatively straightforward. Let's do one more thing inside of our use. So let's go up to the very top, and then we are going to create a private Boolean being used, and this is going to initially be false. And so what we're going to do is we're going to go into our use program. We'll say if not being used, and then we want to use it. Otherwise, we don't need to do anything because it's not being used. And then inside of detach, we will say being used equals false. Also, being used equals true once we start to use it. And this will just be nice because then we can't accidentally use the shader twice. If it's already being used, we don't waste GPU time rebinding a program that's already bound to the GPU. It probably optimizes that away, but I wouldn't count on that 100% sure, so we'll just do this. Then what we can do is inside here, before we do this thing, like I said, we want to make sure we're using the shader. We'll just call it use to make sure we are absolutely using the shader every single time, because you don't want to call this and then not be using the shader that you're trying to use. Then what we're going to do is we're going to create the upload vec for f. We'll try this one. And so we're going to take in a variable name, which is the name of the uniform we're looking for, and we'll take in a vector for f, and we'll just call this vec for f. And then we're going to follow this same exact pattern. We'll say the variable location equals GL get uniform location, shader program ID, and the variable name. So the shader we're using, and then the variable name we're looking for, we'll say use to make sure we're using it, and then we'll say GL uniform matrix, GL uniform 4FV. So for float vector is what that stands for. And then it expects, if you look at this, a location, which is our var location, and then a float buffer or a float array, which is the value, and we could say vec for f dot. And then I did this really simply. Let's actually just change this to vec2, or just vec, because it'll make it a little bit easier. You can literally just say vec.y, vec.x, vec.y, z, and then w, and that should upload it. And don't do the v. 4f, just 4f. Sorry about that. Okay, so that's for vectors. For vec3, you would just change this to a 3, you would change this to a 3, and so on. We'll do another one, public void upload float string, not that string, string var name, and float value. and we'll say int var location equals GL get uniform location, and we will pass in our shader program ID, and we'll pass in the var name. Same thing again, use it, and then we'll say GL uniform 1F, and location is going to be our var location. The float is going to be our value. Okay, you can also do ints and mat3f, and there's another one for texture that we will get to eventually. I'm going to show one of the ints because, well, actually, we're just going to use int. So upload int string var name float, or actually this is going to be an integer value. I'm literally just going to copy this now because it gets very repetitive. These are the only repetitive things that we really have to do too. And we want to do 1i since we're doing an integer. So that should be good. Okay, now I'm going to do the same thing for vec3 and vec2 and matrix 3 and matrix 2. I don't think we do have a matrix 2 actually. Yeah, so just matrix 3. So I'm going to time lapse this real quick because I'm literally just going to be copying and pasting stuff and changing a few different things. All right, so I finished that up real quick. One thing to note, just make sure when you're doing the matrix 3, capacity is 9 for the float buffer, and make sure it changes to 3FV. Don't forget that part. But yeah, so I just sort of created all these, and we should be able to use them now. So let's actually use them and create a shader real quick. If we go back to our level editor scene, you can see we're already uploading 2 uniforms. So we have U projection and U view. Let's upload a third one, and we'll call this one U time. So we'll say upload float U time, and we're going to call this time.getTime. So we're literally just going to pass the time to it because then we can do some time-based animations in our shader, which is kind of cool. And then let's go into default.glsl. Since we pass in time, we now need to accept time. And cool thing about uniforms, you can have it inside of your vertex or inside your fragment. I'm going to do this one inside the fragment because I think it makes a little bit more sense. So I'm going to go uniform, float, and utime. Have to make sure it's the same exact name. Then what we're going to do is we're just going to say color equals sign of utime times the F color. So just going to take the sign of it, which means it should sort of blink on and off the colors. And let's see if that works. And sure enough, it's blinking on and off. But that's not the cool thing we're going to do. We're going to do something even cooler than this because this isn't that interesting. Let's get real here. So I'm going to think of something real quick, come up with a program, and then we're going to implement it. Okay, so we'll do a couple things here just to sort of illustrate the power of shaders. And this still doesn't even like really touch what they can do. So first, what we're going to do is we're going to convert our image to black and white, which is pretty simple. So black and white just means it's the average of all the color. So we'll say f.color.x. Or actually, we can say R, fcolor.g, and F, this shouldn't be commas, this should be plus, fcolor.g plus fcolor.b over 3. So we get the average, and then instead of, oh, that should not be there, that noise, that's what we're going to do in a minute. So instead of just doing fcolor, we'll do average, vec for average, average, and then we'll do 1 for that last one. Then when we output this, we should see black and white, which we get a black and white image now. So it's the same image, it's just been converted to black and white, which is pretty cool. And you can do this with anything. And as you saw, it's 2 lines, just 2 lines to do that. And then it automatically converts everything. So that's one cool thing. Another cool thing, I found this little thing on the internet, and it basically is a noise calculating function, which I think it would be really cool to go in depth into noise specifically. We will not be doing that in this tutorial, but maybe in the future we'll have something that covers all the different, like some different types of noise and everything you can do with that. But what we're going to do is we're going to say fcolor times noise, and this is just some random number generator between 0 and 1 basically is what this does based on a 2-dimensional input, which is our thing. And so these are like sort of seeds that you would have, and then this is just like a modulus almost. So the sign basically clamps it between a certain amount, and then the fraction gets that out of there. So there's a lot in this little one line, but it generates this cool thing that we see here. And you see it's this really cool noise thing that's just going according to the position. And why is it changing as the position moves? Yeah, and honestly, I'm not actually really sure why it's changing as it moves, but it's cool. So a cool noise function. Like I said, in the future, we might go in depth more about this. This is where I got that from too. They have another thing called Perlin noise. You should try and implement it yourself if you really want to, because Perlin noise is used for a lot of different things too. And then if you use Perlin noise with time, you can create some cool looking things like clouds and stuff. So just some cool stuff that you can do with this. But I hope this covers up shaders a little bit more. There are some things that we still didn't really get to very specifically, like how you would create functions and stuff. It's a whole programming language, so it's a lot of stuff. We're going to be using it for like the bare minimum just to get our textures and everything, but shaders are super powerful and you can use them for literally anything. I think some game companies even use like geometry shaders to manipulate hair using physics and stuff. And then they run their physics calculations inside of shaders and everything too. It's insane using the GPU to do a lot of stuff. So hopefully in the future, we'll get to go over a lot more stuff that we can do with this because they are so cool. And I really want to learn how to use them better too. Okay, guys, I hope you liked this. If you did, please hit like and subscribe. In the next tutorial, what we will be going over, we'll probably start going over textures and how to load a texture, which is just an image, into our game so that we can start using that. So I'll see you guys then. Thanks. See you.